Dear student, previous class I discussed about the introduction of coordination chemistry, coordination, compound, salt, types of salt, ligand, types of ligand, and some important points related to the coordination compound. Now I will discuss about the Werner's coordination theory. Werner's coordination theory generally used for to explain the structure of coordination compound. Suppose I will take a coordination compound CO NH3 6Cl2. This is a coordination compound. Our aim to draw the structure of this coordination compound. This can be possible by the help of Werner's coordination theory. At first, I will discuss postulates of Werner's coordination theory. According to the Werner's theory, the central atom cobalt exhibit two types of valency. One is your primary valency. Second is your secondary valency. Every central metal atom in coordination compound exhibit two type of valency. One is your primary valency, another is your secondary valency. Primary valency also called ionizable valency. Primary valency corresponds to the oxidation state, while secondary valency corresponds to the coordination number. Second point is every central metal atom or ion in coordination compound is fixed. That means secondary valency is fixed. Third point is primary valency is satisfied by negative ions, while secondary valency is satisfied by ligand. Fourth point is your primary valency are non-directional, while secondary valency are directional. The directional character of secondary valency shows that secondary valency directed towards a particular direction in space. Fifth number point is your primary valency denoted by dotted line, while secondary valency denoted by bold line. These are the postulates of Werner's coordination theory. By the help of Werner's coordination theory, now I will draw the structure of this coordination compound. There are 6 ligands are present, and the 6 ligands coordinate to the central metal atom or ion through 6 coordinate bond. So the secondary valency of cobalt is your 6. On the other hand, the primary valency here is your 2 because your 2 negative ions present, that means 2 Cl minus ion are present. We know that the secondary valency are directed in a particular direction in space. So now I will write here cobalt, and the 6 secondary valency are directed in such a way that they make a geometry. Suppose I will draw the 6 secondary valency like this. We know that the secondary valency are denoted by bold line, and another 2 secondary valency are drawn like this. Here one secondary valency, on the back side of whiteboard another secondary valency is present. This is a 3-dimensional structure, but the whiteboard is 2-dimensional structure, so it is bound to draw like this. of the whiteboard. This is a three-dimensional structure, but it is represented on 2D whiteboard. By joining the line, we can able to form a octahedral like this. The sixth secondary valency arranged like this. There are two primary valency are present. So I can represent the primary valency by the help of dotted lines. Suppose here a primary valency is present, another is present here. The secondary valency connected to the ligand with the central metal atom. So here I can write NH3, here also I can write NH3, here also I can write NH3, here I can also write NH3, here also NH3 is present, here also NH3 is present. This is the structure of this compound according to Werner's theory. This is your compound number 1. Suppose I want to draw the structure of compound number 2, that is CO, NH3, 5Cl, Cl2. Here 6 ligands are present, so the secondary valency is 6. The primary valency of this central metal atom is 3, because we know that primary valency corresponds to the oxidation state, and the primary valency also satisfied by negative ions. So according to the structure of the compound, there are 3 negative ions are present, so the primary valency is 3. Now I want to draw the structure of this compound. Here 6 secondary valency are drawn like this, but 5NH3 is attached with the 5 secondary valency, and the remaining secondary valency is attached with the chlorine. The chlorine atom attached to the central metal atom or ion like this. Here chlorine play 2 roles, that is your one is your ligand, another is your negative ions. So chlorine have contribution towards the secondary valency and also contribution towards the primary valency. So it is bound to give the dotted line here to represent the primary valency, and also give bold line to represent the secondary valency. Suppose I want to draw the structure of compound number 3, that is your CO, NH3, 4Cl2, Cl. Here the secondary valency is your 6, primary valency is also 3. The 6 secondary valency are drawn like this. 4 NH3 are attached like this. Here chlorine atom is present, and this chlorine atom play 2 roles. One is your ligand, another is your negative ions. So here also it is bound to give the dotted line, because here 2 chlorine atom present, and the 2 chlorine atom have both contribution towards the secondary valency and the primary valency. Here 1 chlorine atom is removed, because only 1 chlorine atom have contribution towards the primary valency only. This chlorine atom have contribution towards only primary valency. This is the structure of this compound according to Werner's theory. Next I will explain about the demerits of Werner's theory. Werner's theory unable to explain the properties like color, magnetic property, structure of coordination, compound. Werner's theory unable to explain the color, magnetic character and structure of coordination compound. Second point is Runners theory do not have justification for his proposed theory. Next I will discuss about the merits of Runners theory. It gives the exact formula of a coordination compound. Second point is it explains the structure of coordination compound having coordination number 4 and coordination number 6. Coordination number 4 gives the tetrahedral or square planar structure of coordination compound. Coordination number 6 corresponds to the octahedral structure of coordination compound. This is all about the Varna's coordination theory. Now I will discuss some questions related to the coordination number and oxidation number. First question is find the coordination number and oxidation number in CONH3 5Cl Cl2. In this compound 6 ligand is present. Among the 6 ligand 5 is your NH3 and 1 is your chlorine, and the 6 monovalent ligand attached to the central metal atom or ion with 6 coordinate bond. So the coordination number of cobalt equal to 6. Now I will find the oxidation number of cobalt in this compound. Suppose the oxidation number of cobalt is your X. Remember an important point: the oxidation number due to the coordination entity plus oxidation number due to the counter ion is equal to 0. Here the counter ion is your chlorine. Here chlorine is present in Cl minus form. So the oxidation number due to 2Cl minus is your minus 2. So here it is bound to write plus 2. The plus 2 is for the coordination entity. Plus 2 plus minus 2 equal to 0 because it is a neutral molecule. Now the plus 2 is equal to the oxidation number of cobalt plus 5 into oxidation number of NH3 plus 1 into oxidation number of chlorine. So here I can write X plus 5 into oxidation number of NH3. We know that oxidation number of NH3 is 0 because NH3 is a molecule. So here I can write 5 into 0 plus oxidation number of chlorine. Here chlorine is present in Cl minus form. So the oxidation number of chlorine here is minus 1. So here I can write 1 into minus 1 equal to plus 2. So here I can write X plus 0 minus 1 equal to plus 2. Imply that X is equal to plus 2 plus 1. That is going to imply that X equal to plus 3. In our question, find the coordination number and oxidation number of cobalt in this compound. So I can write coordination number of CO equal to 6, oxidation number of CO equal to plus 3. Next I will solve another question. Find the oxidation number and coordination number of iron in FeNH3 twice En twice Cl2. Here En means ethylene diamine. This is a bidentate ligand, that means this ligand connected to the central atom iron by two coordination bond. There are two En, means there are four coordination bond due to two En. Here two monodental ligand are present, that means two coordinate bond is due to two NH3 ligand. That means there are totally 6 coordination bond. As a result, the coordination number of iron in this compound is 6. Now I will find out the oxidation number of iron in this compound. Let the oxidation number of iron in this compound is your X. We know that chlorine having -1 charge, that means here I can write -2. As a result, this part is your +2. We know that the oxidation number of NH3 is your 0. It is also a molecule, so the oxidation number of En means 0. As a result, I can write X into 1 plus 2 into 0 plus 2 into 0 equal to +2. Imply that X plus 0 is equal to +2. Imply that X is equal to +2. So I can write coordination number of iron equal to 6. Oxidation number of iron equal to +2. Next I will do another question. Find the number of ions in FeCO5Cl2. When this compound undergoes dissociation, then it gives 3 ions. One is your FeCO5Cl2 plus, another 2 is your 2Cl minus. So there are totally 3 ions. So our question, find out the ions. So the number of ions equal to 1 plus 2, that is your 3. Next I will discuss about the nomenclature of coordination compounds. Suppose I will take an example of coordination compound CO NH3 6Cl3. What is the name of this coordination compound? Suppose I will take another example, PT NH3 twice Cl2. This is your first example, this is your second example. What is the name of this compound and what is the name of this compound? For naming such type of compound, we generally follow certain rule. This is an ionic coordination compound. This is your non-ionic coordination compound. Ionic coordination compound, two type, one is your cationic, another is your anionic. This is your cationic coordination complex. This is your non-ionic coordination compound. Suppose I will take another example, K3 FeC2O4 thrice. This is also an ionic coordination compound, but it belongs to anionic complex. Remember the first rule. For naming ionic coordination compound, it is bound to write the cationic part first, then the anionic part. This is your an ionic coordination compound. This is also an ionic coordination compound. That means according to this rule, this part is named first, then this part. Similarly, this part named first, then this part. Second rule is your, for naming non-ionic complex, the name of the non-ionic complex must be written in one word. Third rule is your, for naming the coordination sphere part, the name of the ligand is written first, then the name of the central metal atom or ion, then the oxidation state of the central metal atom or ion. Remember, the oxidation state always written in Roman letter, that is your, if oxidation number of the central metal atom or ion is your 0, then it is written as 0. If the oxidation number is your +1, then it is written as I. If the oxidation state is your +2, then it is written as I. If the oxidation state is your +3, then it is written as III. Like that, I can also write IV, V, like this. The oxidation state of the central metal atom is written in a parenthesis bracket. Next rule is your, the name of the negative ligand and with the ITO, ATO, IDO instead of IT, AT, IDE. Suppose I will take some negative ligand. Name as ligand. Cl minus is a negative ligand, that is said to be chloride. If the Cl minus is used as a ligand, then it is named as chlorido. Look at that. Here Cl minus is present, but here Cl is not used as a ligand because it is present outside the coordination sphere. Look at that. Here chlorine is used as a ligand. So for this case I can write chlorido, but for this case I can write chloride. Like that, suppose I will take SO4 2 minus. This is also a negative ligand. The name of this negative ligand is your sulfate. If this negative ligand is used as a ligand, then I can write sulfato. Similarly, suppose I will take S2 minus. This is said to be sulfide, and if it will used as a ligand, then it is named as sulfido. Look at that. Instead of ID, I can write IDO. Instead of AT, it is bound to write ATO. Instead of IDE, I can write IDO. So remember, negative ligand ends with the ITO, ATO, IDO instead of IT, AT, ID respectively. Next rule is the positive ligand ends with the IUM. Suppose I will take some example of positive ligand. Positive ligand, name as ligand. Suppose I will take a positive ligand, that is your Cl plus, that is said to be chloronium ion. If Cl plus is used as a ligand, then I can write NO plus, its name is nitrosonium. If it is used as an ligand, then it is written as nitrosonium. Actual name is nitrosonium ion. If it is used as an ligand, then I can write nitrosonium. Similarly, NO2 plus, that is nitronium ion, and if it will used as a ligand, then I can write nitronium. Next rule is the neutral ligand. The neutral ligand is written as such as. That means, suppose I will take a neutral ligand, that is PH3. The actual name of PH3 is phosphine. If PH3 is used as a ligand, then I can write also phosphine in the name of the coordination compound.
Similarly, C5H5N
said to be pyridine. If I will use this as a ligand, then I can also write pyridine. Similarly, I can take another example, CH3NH2. The name of this compound is said to be methylamine. If this compound is used as a ligand, then I can also write methylamine. In case of neutral ligand, the name is written as such as. There are many ligands which belongs to neutral ligand. It is bound to remember the name of different types of ligand and the rules regarding about the ligands. There are some exceptional cases also found. For example, water is a neutral ligand, but if water is used as a ligand, then we cannot write water in the nomenclature of the coordination compound. We can write aqua. These are considered as the exceptional case. Like that CO, that is said to be carbon monoxide. If this is used as a ligand, then I can write carbonyl. Similarly, for NO, I can write nitrosyl. This is your nitric acid, but it is bound to write nitrosyl in the nomenclature of the coordination compound. Similarly, NH3, that is said to be ammonia, but if this compound is used as a ligand, then it is bound to write amine. Next rule is if two or more same type of ligands are present in a coordination compound, then it is bound to write the prefix di for 2, tri for 3. You can also write tetra, penta, hexa like this. Look at that, here 6 ligands are present, so it is bound to write hexaamine. Remember an important point, the name of this coordination compound or any coordination compound always written in small letter. Next rule is there must be some gap between the name of the coordination entity part and counter ion part. Remember also another rule, if a complex belongs to anionic complex, then the name of the central metal atom end with the AT. On the other hand, if the complex belongs to neutral or cationic, then the name of the central metal atom name is such as. There are some special cases which arises in the nomenclature of the coordination compound. For example, for anionic complex, we use the word At with the Latin name of the central metal atom. For example, iron, we cannot write ironate, it is bound to write ferrate. The word ferrate comes from ferrum. Similarly, if silver is present in an anionic complex, then it is bound to write arsenate. Similarly, for copper, we can write cuprate. For tin, we can write stannate, like this. But remember, if the iron is present in an cationic complex, then simply I can write iron. I cannot write ferrum. If the metal gold is present in anionic, then I can write aurate. If the gold is present in cationic complex or neutral complex, then it is bound to write only the word gold. Don't write aurum. Similarly, if silver is present in anionic complex, then it is bound to write arsenate. If silver is present in cationic or neutral complex, then it is bound to write silver. This is the exceptional case which generally arises in that element which having Latin name. Suppose I will take an example Fe NH3 6Cl3. Look at that. In this case, iron present in anionic complex, but in this case, iron present in the cationic complex. In this case, the name of the central metal atom must be written as ferrate, but in this case, the name of the central metal atom written as simply iron. Now I want to write a name for this compound. This belongs to ionic complex. We know that in ionic complex, the name of cationic part is written first, then the name of anionic part will be written. This is your cationic part, this is your anionic part. So the name of this part is written first, then the name of this part will be written. This is your coordination sphere part. That means in coordination sphere part, the name of the ligand is written first, then the name of the central metal atom or ion, then oxidation state, then the counter ion. Here the ligand is your NH3. This belongs to exceptional case. That means here I can write amine. There are 6 NH3 ligand present, so it is bound to write hexaamine. Remember one point, the name of this compound must be written in small letter, and there is also a gap between this part name and this part name. So at first I will write hexaamine. Next I will write the name of the central metal atom. Here the central metal atom present in cationic complex. So the name of the central metal atom is written as such as, that means I can write cobalt. Then I will write the oxidation number of the central metal atom. We know that this is your Cl minus, so it is bound to write here -3. We know that the oxidation state of this part plus oxidation state of this part is equal to 0, so it is bound to write +3. Let the oxidation number of cobalt is your X. We know that the oxidation number of NH3 is 0 because NH3 belongs to molecule, so I can write X plus 6 into 0 equal to +3, implies that X is equal to +3. In this compound, the cobalt having oxidation state, that is your +3, so it is bound to write III. According to the rule, we know that for +3, the Roman letter is your III. This is the name of this coordination sphere part. Now I will write the name of the counter ion. Here Cl is present in the form of Cl minus. We know that Cl minus means chloride. So I can write here chloride. There must be a space between the name of this part and this part. This is your belongs to coordination entity part. This is your belongs to counter ion part. The name of this compound is your hexaamine cobalt triple I chloride. Look at that here, plus 3 is present on the coordination sphere, so this belongs to your cationic complex. Now I can write the name of this compound, that is your hexaamine. Here the central metal atom is your iron. Iron is present in the cationic complex, so I can write iron. Now I will write the oxidation state of iron. Look at that here, Cl minus is present. There are 3 Cl minus is present, so it is bound to write here minus 3. It is bound to write plus 3 on the coordination sphere. Suppose the oxidation state of iron is your X. We know that the oxidation state of NH3 is your 0. So I can write X plus 0 into 6 equal to plus 3. Where X is equal to plus 3. Since the oxidation number of iron is your plus 3, so it is bound to write your triple I. Now your Cl minus is present. This is not belongs to your ligand, so I can write simply chloride. The name of this compound is your hexaamine iron triple I chloride. Remember another rule: if 2 or more different types of ligand are present, then the ligands are written in alphabetical order. Look at that. In this case, 2 NH3 ligand are present and 2 Cl minus ligand are present. The name of NH3 is your amine. The name of Cl minus is your chlorido. This belongs to a non-ionic complex, so the name of this complex is written in one word. In this complex, there is no counter ion part, only coordination entity part is present. In this complex, according to the rule, the name of ligand is written first, then the name of the central metal atom, then the oxidation state of the central metal atom. There are 2 different types of ligand is present. One is your NH3, another is your Cl minus. According to the rule, amine is written first, then chlorido will be written because the letter A comes first. Accordingly, alphabetical order. There are 2 NH3 are present, so it is bound to write diamine. Next is your dichlorido. Next I will write platinum because platinum belongs to the neutral complex. Diamine dichlorido platinum. This is your neutral complex, so it is bound to write 0. Our aim to find out the oxidation state of platinum. We know that NH3 belongs to a neutral molecule, so here I can write 0. Here Cl is in the form of Cl minus, so it is bound to write minus 2 because 1 Cl minus having oxidation state is your minus 1. There are 2 Cl minus, so it is bound to write minus 2. Now I can write X plus 0 into 2 minus 1 into 2 equal to 0. That means I can write X plus 0 minus 2 equal to 0. That X is equal to plus 2. Since the oxidation state of platinum is your plus 2, it is bound to write double I here. The name of this compound is your diamine dichlorido platinum double I. Suppose I will take another example: Fe, NH3 twice, En twice, Cl2. This is your another example. What is the name of this coordination compound? Here En means ethylene diamine. There are 2 En is present. For 2 we generally use bi. For 3 generally we use tri. For 4 we generally use tetra like this. Look at that. In this type of ligand, already the ligand contain the prefix like
dye.
So for such type of ligand, we generally use the special type of prefix, that is bis for 2, tris for 3, tetrakis for 4, pentakis for 5, like that. Remember an important point. If a ligand contain the prefix like di, tri, tetra, etc., then for such type of ligand we generally use the prefix like bis, tris, tetrakis, like this. Remember an important point, when the ligands are arranged in alphabetical order, don't consider about the prefix like bi, tri, tetra, also the prefix like bis, tris, tetrakis, like that. Your two types of ligand are present. One is your NH3, another is your En. NH3 means amine, En means ethylene diamine. A comes first accordingly alphabetical order. So I can write diamine, bis, ethylene, diamine. It is bound to give a parenthesis bracket like this. Here the iron is present in the cationic complex, so it is bound to write the word iron. Next I will write the oxidation state of iron. Look at that. Here I can write -2. Here I can write +2 on the coordination sphere. We know that the NH3 is a molecule, so I can write 0 for NH3. En is also a molecule, so I can write 0 here. Suppose the oxidation state of iron is your X. Now I can write X plus 2 into 0 plus 2 into 0 equal to +2. Implies that I can write X is equal to +2. So here I can write double I. This is your coordination entity part. Now I will write the counter ion part by taking some space. Your Cl minus ion is present, so I can write your chloride. The name of this compound is your diamine bis ethylene diamine iron 2 chloride. I can also write a name for this compound, that is your diamine bis. In bracket I can also write En for ethylene diamine. Then I can write iron double I chloride. You can write the name of the ligand, or you can also write the symbol of the ligand. Remember an important point, some complicated organic compounds are also represented by the symbol, just like ethylene diamine is symbolized as En. Similarly, I can write a symbol for triethylene tetraamine, that is your TRIEN. Similarly, I can write a symbol for diethylene triamine, that is your DIEN. For thoria, I can write TU. For urea I can write EU. For pyridine I can write PY. For oxalate I can write OX. There are a large number of complicated organic compounds which are written in their symbol form.
Suppose I will take an example like this: NH3,4CO, OH, NH2, CO, NH3,4, SO4.
This is your a coordination compound. Your bridging ligand is present. The bridging ligand is your OH, another is your NH2. When I will write the name of this bridging ligand, then I can use the mu symbol before the name of this bridging ligand. That means it is bound to write mu hydroxido, another is mu amido. Don't write mu amine because your amine is not a bridging ligand. Your OH and NH2 act as a bridging ligand. Now I can write the name of this coordination compound like this: tetraamine cobalt. Your cobalt belongs to the cationic complex, so simply I can write your cobalt. Next I will write the oxidation number of cobalt. We know that this is your sulfate, that means here I can write -2. As a result, it is bound to write here +2. OH belongs to negative ligand having -1 oxidation state. Amide having also oxidation state, that is -1. Suppose this is your X, this is also your X. The oxidation state of NH3 is your 0. The oxidation state of NH3 is your also 0. By calculation, we can able to find out the oxidation state of cobalt is your 2. So here it is bound to write II. Next I will write the bridging ligand. Here mu hydroxido is present. Another is mu amido is present. Mu amido is written first, then mu hydroxido will be written because A will comes according to the alphabetical order. So next I will write by giving a hyphen mu amido, mu hydroxido. Again I can continue the name tetraamine cobalt II sulfate. Remember, there is no space between hydroxido and tetraamine. There is only gap between this part and this part. I can also write a short name for this compound. There are 8 NH3 present, so I can write octaamine mu amido mu hydroxido dicobalt II sulfate. There is a space between cobalt II and sulfate. This can also minimize. We can also write mu amido mu hydroxido bis tetraamine cobalt II sulfate. Suppose I will take an example in which ambident ligand is present. Zn HCN for 2 minus, another is your Zn NCS for 2 minus. Your HCN NCS are called ambident ligand. Your sulfur coordinate to the zinc. On the other hand, your nitrogen coordinate to the zinc. When I will write the name, then I can write thiocyanato hyphen S because S coordinate to the zinc. Similarly, when I will write the name of this ligand, then it is bound to write thiocyanato N because N coordinate to the zinc. Similarly, I can write bond NO2. For this ligand, I can write nitrito hyphen N because N will coordinate with the central metal atom or ion. On the other hand, for bond ONO, it is bound to write nitrito O because O will attach the central metal atom through coordinate bond. The name of this complex ion is tetrathiocyanato S zincate because zinc is present in an anionic complex ion. For ionic complex, it is bound to write the word ion. There must be a hyphen between S and zincate. The name of this complex ion is tetrathiocyanoto-N-zinc ion. It is bound to write the oxidation number of zinc, that is your II. Here it is also bound to write II to indicate the oxidation state of zinc in this complex. Finally, I can write a name for this complex ion, that is your tetrathiocyanoto-S-zincate ion. For this complex, I can write tetrathiocyanoto-N-zincate ion. Suppose I will take another example, platinum NH3 4, platinum Cl4. What is the name of this coordination compound? This is a one type of coordination compound in which both cation and anionic part are complex. That means cation is a complex ion. On the other hand, also anion is also a complex ion. For naming such type of coordination compound, generally the complex cation is written first without any characteristics ending. Then the
complex anion part will be written
with the name of metal, and the name of metal must be end with the word AT. Also here oxidation number of the metal is written. We know that NH3 is a molecule, so the oxidation number of NH3 is 0. Here Cl minus ion is present. We know that the oxidation number of Cl minus is -1. As a result, here I can write -4. We know that platinum exhibits in two oxidation state. One is your +2, another is your +4. If I will take the oxidation number of this platinum is your +2, then the oxidation number of this platinum is your +4. If I will take the oxidation number of this platinum is your +4, then the oxidation number of this platinum is your +2. If this is your +2, then it is bound to write here +2, because this part gives a -2, that means this part must be your +2. From this it is clear that this is your cationic part, this is your anionic part. According to the rule, this part is named first, then this part. At first I will write the name of the ligand. Here NH3 is present, there are 4 NH3 are present. So I can write tetraamine platinum 4. Next I will write the anionic part, tetrachlorido platinate II. There is no gap between tetrachlorido and platinum. The name of this complex is your tetraamine platinum IV tetrachlorido platinate II. Next I will discuss about the nomenclature of geometrical isomer. Generally we think about cis and trans isomer. At first I will discuss about the geometrical isomer in square planar complex. In square planar complex, the metal is present like this and the ligands are present like this. Suppose this is your ligand number 1, this is your 2, this is your 3, this is your 4. In octahedral complex, the metal is present like this. Suppose this is your ligand number 1, this is your 2, this is your 3, this is your 4, this is your 5, this is your 6. This is your square planar complex, this is your octahedral complex. Cis isomer means the same ligand present in the adjacent position. Trans isomer means the same ligand present in the opposite position to each other. In this case, case 1, 2, 2, 3, 3, 4, 4, 1 are called cis isomer. On the other hand, 1, 3, 2, 4 are called trans isomer. In this case, 1, 2, 2, 3, 3, 4, 4, 1, 1, 5, 2, 5. Like that, you can also think about other cis isomer. These are considered as cis isomer. In this case, 1, 3, 2, 4, 5, 6 are called trans isomer. Suppose I will take an example. What is the name of this complex ion? This belongs to trans isomer. The name of this complex ion is your di-aqua dichlorido platinate IV ion. If I will take another example, the name of this complex ion is also di-aqua dichlorido platinate IV ion. But there is a difference. It belongs to cis isomer. It belongs to trans isomer. So here it is bound to write trans di-aqua dichlorido platinate IV ion. It is bound to write here cis di-aqua dichlorido platinate IV ion. Take another example. Cl En twice Pt bond Pt En twice Cl Cl2. This is one type of coordination compound in which metal bond is present. For naming such type of coordination compound, we generally use the prefix bi before the name of metal. The name of this compound is your dichlorido base En biplatinum double I chloride. Suppose I will take another example. Cr H2O 4 Cl2 Cl dot 2H2O. This is an example of water of crystallized. For naming such type of compound, generally we use some extra word for this water molecule. The name of this part is your tetra aqua dichlorido chromium IV chloride. For this water molecule, I can write -2 water. If 3 water molecule is present, then I can write -3 water. If 4 water molecule is present, then I can write -4 water. It has also other name, that is your tetra aqua dichlorido chromium IV chloride dihydrate. If there are 3 water molecules present, then I can write trihydrate. If there are 1 water molecule is present, then I can write monohydrate. This is all about the rules for naming a coordination compound. Next I will explain about the rules for writing formula of a coordination compound. Suppose I will take an example, tetra aqua di chlorido, chromium, triple I nitrate. What will be the formula of this coordination compound? For writing the formula of this coordination compound, we generally follow some rules. First rule is the formula of cation for simple or complex is written first, then the formula of anion. Second is when the formula of complex is written, then the complex ion part is written in a square bracket. In the square bracket, the metal atom or ion is written first, then the ligands are written. The ligands are arranged in the following sequence. At first, the negative ligand is written, then the neutral, then the positive ligand. This is the order of ligands which will be written in the square bracket after the symbol of metal or atom. If more than one same type of ligand are present, then they are arranged according to their alphabetical order. Third rule is the abbreviation of polydentate ligand and the formula of polyatomic ligand must be enclosed in a parenthesis bracket. But remember, there is no separation between the ligands. Fourth rule is there is no space between the metal and the ligand. Fifth rule is the charge of complex ion must be written in the right superscript with the sign plus or minus, which are enclosed in parenthesis bracket. Sixth rule is the number of cation or anion to be written in the formula of the coordination compound is calculated on the basis that the total positive charge of the cation is equal to the total negative charge of the anion. These are the rules for writing formula of a coordination compound. Now I will apply the rules for this coordination compound to write the formula of the coordination compound. Here the positive part is this, here the negative part is this. The positive part is complex ion part. In complex ion part, the metal is written first, then the ligand. Here the metal is chromium. So it is very important to write first chromium. There are two types of ligand are present. One is water, another is chlorine. Here water is a neutral ligand. Cl minus is a negative ligand. According to the rule, at first negative ligand written, then the neutral, then the positive ligand. So Cl minus is written first. That means I can write Cl twice, H2O twice. We know that there is no gap between the metal and the ligand, and also there is no gap between the ligand and ligand. And we again know that the polyatomic ligand must be enclosed in a parenthesis bracket. Now I will give a square bracket like this. Then I can write the anionic part. The anionic part is your nitrate. The formula of nitrate is your NO3. Now I can write the number of cation or anions in the coordination compound. This can be calculated on the basis that the total positive charge of the cation is equal to the total negative charge of the anion. This is your positive part, this is your negative part. Your chromium having oxidation number 3. So here I put plus 3. Chlorine have minus 1, that means totally minus 2. Water having no charge, so here I will put 0. The total charge which will be written on the right superscript of the coordination sphere is your plus 1. We know that nitrate having charge minus 1. Now look at that plus 1 and here minus 1 is present. That means they are equal. So there is no necessary to write any numbers for cation and anionic part. So the formula is your CrCl2H2O twice NO3. Next I will take another example for writing formula of a coordination compound. The compound is your dichlorido tetraamine cobalt triple ion. What will be the formula of this compound? At first I will write the central metal atom. That means I can write CO. There are two types of ligand. One is your negative ligand, another is your neutral ligand. We know that negative ligand written first, then the neutral ligand. So here I can write Cl2 NH3 4. Then I will give the square bracket. This is your an ion. So it is bound to write here some charge. Cobalt having +3 oxidation state. That means here I can write +3. Chlorine having -1. That means here I can write -2. NH3 is a neutral. So here I can write 0. That means here I can write +1. That means finally I can write COCl2 NH3 4 +1. This is the formula for this complex ion. Suppose I will take another example, hexaamine platinum IV chloride. What will be the formula of this coordination compound? Here the central metal atom is your platinum. So I can write Pt. Here the ligand is your NH3. There are 6 ligands are present. So here I can write NH3 6. Then it is bound to give the square bracket. Here chloride is present. So here I can write Cl. Now write the number of cation and anion. Chloride having charge -1. Platinum having +4, NH3 having 0. That means here it is bound to write +4. To balance the charge, it is bound to write here 4. That means after writing the 4 here, now the negative charge is your -4. Now look at that. Here +4, here -4. That means the formula of the complex compound is your PtNH36Cl4. This is all about the nomenclature of coordination compound. Next I will explain about the EN rule. EN rule means effective atomic number. According to this rule, every central metal atom or ion in a complex compound must have a tendency to gain the effective atomic number of next inert gas. Suppose I will take an example K4FeCN6. Here I can write +4. There are 4 K plus are present. We know that each K plus ion having charge +1. That means 4 K plus ion having 4 plus. Then it is bound to write here -4. We know that Cn having charge -1. There are 6 Cn. So here I can write -6. As a result, iron having +2 charge. As a result, the oxidation number of iron is your +2. Coordination number of iron is your 6 because your 6 ligand is present. The ligands are monovalent ligand. So the coordination number of iron is your 6. Mathematically, effective atomic number equal to atomic number of the central metal atom or ion minus oxidation number +2 into coordination number. Atomic number of iron is your 26. Oxidation number of iron is your 2. Coordination number of iron is your 6. By solving, I can write 26 minus 2 plus 12. Finally, the effective atomic number is equal to 36. This is the atomic number of krypton. From this it is clear that every central metal atom or ion in a coordination compound must have a tendency to gain the effective atomic number of next inert gas.